The third method of propagation, the skywave, uses the ionosphere. We will look at satellite propagation in its own lesson. Let's start with surface waves. These exist at frequencies from about 20 kHz to about 50 MHz, which is from the upper end of very low frequency through long wave, medium wave and high frequency to the lower end of very high frequency. They travel across the Earth by the process of diffraction. The range achievable is dependent upon several factors. As the radio wave frequency increases, surface attenuation increases. Surface waves are effectively non-existent above high frequency, that is, above 30 MHz. Surface waves are therefore used in the low frequency for NDB transmissions, in the medium frequency for NDBs and long-range communications, and in the high frequency for long-range communications. The second type of non-ionospheric propagation is the space wave, which is made up of two parts, a ground-reflected wave and a direct wave. At frequencies of VHF and above, radio waves start to behave more like visible light, and in the same way that light has a visible horizon, radio waves also have a horizon. So the only propagation at these frequencies is line of sight. There is some atmospheric refraction, which causes the radio waves to bend towards the Earth, and this does increase the range slightly beyond the geometric horizon. But as radio frequency increases, refraction reduces. The range of a space wave can be calculated by this formula. Range in nautical miles is 1.23 times the sum of the square roots of the height in feet of the transmitter above the ground and the height of the receiver in feet. So, suppose the transmitter is at 1600 feet above mean sea level and the aircraft is at 22,500 feet. Their square roots are 40 and 150, respectively. Multiplying by 1.23 gives us the answer 233.7 nautical miles. Let's move on then to ionospheric propagation, and we'll start with a look at what the ionosphere is made of. The Earth's atmosphere is made up of different layers containing progressively fewer atoms of gases with height above the Earth. From a height of about 50 kilometers up to 400 kilometers, the atmosphere is also designated as the ionosphere, because ionization takes place there. It is divided into three layers, D, E, and F. Ionization is the process by which negatively charged electrons are dislodged from the outer shells of an atom by ultraviolet light from the sun, leaving the atom with an imbalance of positive ions. When gas is in this state, it is known as plasma. The extent of the ionization is such as to create bands of negatively charged electrons, and it is these bands, or layers, which refract radio waves. Ultraviolet light waves of different frequencies penetrate the atmosphere to a different extent, creating bands of ionized gases at different levels. Because ionization is dependent upon the sun's energy, it is greater during the day than at night. There are three distinct layers in the ionosphere, called D, E, and F. Layer F divides into two layers during the day, called F1 and F2, but they recombine at night. Layer D is found at an average height of 75 kilometers in the atmosphere. Ionization is low, because it is the lowest region of the atmosphere to be ionized. It has the limited ability to refract signals of low frequencies, but the waves of most frequencies are attenuated or pass through it. At night, the negative electrons and the positive ions recombine, and the D layer disappears until the next sunrise. The E layer, also known as the Kennelly Heaviside layer, after its discoverers, is found at an average height of 125 kilometers. Normally, the layer can only reflect waves having a frequency lower than about 10 MHz, and it has a negative effect on wavelengths above 10 MHz due to its partial absorption of these waves. At night, the electrons and ions begin to recombine, doing so more quickly at lower levels where the sun's radiation is lost first. Consequently, the E layer is effective at a greater height for a while at night, and is able to refract waves further than during the day. The F layer, also known as the Appleton layer, exists at an average height of 225 kilometers. During the day, the layer divides into two, known as F1 and F2, because the different frequencies of radiation from the sun ionize the gases to a different extent. At night, there is only one F layer, which is narrower than the combined width of the daytime layers. The ionization in the F layers is quite intense. Consequently, these layers are responsible for most skywave propagation of radio waves, facilitating high-frequency radio communications over long distances. This frequency band is commonly known as shortwave and lies between 3 and 30 MHz. During the summer, as the sun shines more directly on the Earth, the F2 layer is higher, and so radio waves will be refracted further. When a radio wave is transmitted into an ionized layer and it returns, it is called a skywave. The refraction or bending of the wave occurs because there is an abrupt change in the velocity of the upper part of the radio wave as it strikes this new medium of plasma. The ionosphere layers are less dense, with electrons at their outer edges, so it is at the center of these bands that the greatest refraction occurs. Radio waves do not always refract and return to Earth somewhere. The angle at which the aerial points is critical. If the wave is transmitted vertically, it may pass straight through the ionosphere and out to space. By increasing the angle from the vertical, an angle is reached called the critical angle when refraction occurs, and this is called the first returning skywave. But there will be many returning skywaves because radio waves fan out from the transmitter and they will reach the ionosphere at different places, and therefore they will return to Earth in different places. The distance from the transmitter to the point where the first returning wave comes back to Earth is called the skip distance. There is one other term that has to be known, and that is dead space. We have seen that surface waves will only travel out as far as the point where they become so attenuated that they can no longer be detected. The distance from this point to the skip distance is called dead space because no transmission is being received there. We know that the density of free electrons in the ionosphere varies. At a given frequency, as ionization increases, the critical angle for transmission can be less, and this has the effect of reducing the skip distance. And as the surface wave distance remains the same, the dead space will reduce.